Hello students, I am Professor Isha Megarata from LG Institute of Engineering and Technology. We have started with the last chapter of our syllabus, that is light semiconductor interaction. Until now we have covered Einstein's theory, semiconductor laser, joint density of states. We have also seen what is photovoltaic effect, and on the basis of photovoltaic effect we have seen what a solar cell is. So complete construction, working, losses, remedies and applications of solar cell was covered in the last video. In today's video, we will be discussing about Drude model. Now, Drude model, a part of it was covered in the chapter Electronic Materials, where we covered what free electron theory is. Rather, I would say this is a model which is based on the first free electron theory proposed, that is the classical free electron theory, which was proposed in the year 1900. So let's start with Drude model and see what exactly Drude model is. Drude model was proposed in the year 1900 by Paul Drude. So what does the Drude model say? It was proposed to explain the transport properties of materials. What do you mean by the word transport properties? Transport properties are the properties which deal with the flow of charges in materials. If you talk about metals, the charges will only comprise of electrons. On the other hand, if we discuss semiconductors, the charge carriers include electrons and holes both, because semiconductors are the materials which have flow of electrons and holes as well. Now let's move ahead and see what basically a Drude model is. It is a model which considers a metal to be formed of a collection of positively charged ions from which electrons have detached to form an electron gas surrounding the iron core. If you consider a metal is a material which has free electrons. From where these free electrons come? Free electrons are actually the valence electrons which have detached from the atom, and then they move surrounding the atom like an electron gas is moving in the iron core. Now, because we say that electron has moved from the atom, it behaves like a positive ion, and that is the reason we say that these electrons surround the iron core and they behave like an electron gas or an electron cloud. If you remember, this was the basic assumption on which the Drude model or the free electron theory was based. They behave that metals have electrons moving like gas molecules. So now let's move ahead and see what were the basic assumptions of this Drude model. Starting with the first assumption, which says electrons in a metal behave like molecules of an ideal gas where there is no Coulombian interaction and collision between the particles. Now this basically is known as an independent electron approximation. Just have a look at the diagram. In the diagram you can see the red colored circles indicate the positive ions from which the electrons have moved, and the blue colored circles surrounding indicate the electrons which are randomly moving because no external force is being applied. Now, if I say that electrons, that was the assumption of Paul Drude, that electrons are behaving like gas molecules, so they are supposed to follow all the laws of classical theory or the kinetic theory of gases, and that is the reason he said that there is no Coulombian interaction and collision between the particles. If the electrons collide, they will be resulting into an elastic collision, that means transferring the energy to the third particle. No electron will attract the ion present here, or it will not attract the boundary of the material. That is the reason we say it is an independent electron approximation. Moving on to the next assumption, this assumption says electrons collide with the ions and they change the direction and velocity. Let's see what exactly happens. You can just see in the diagram that the electrons are colliding with the atoms, and randomly they are moving in different directions. This is the particular situation when no electric field is applied. Let us discuss the third assumption, which says electrons reach thermal equilibrium by collisions with ions, and their mean kinetic energy is given by half mv square is equals to 3 by 2 kBT. This is the equation which is based on the kinetic theory of gases, which says that kinetic energy increases with temperature. So in this point, I can explain that once the electrons have collided, they move randomly. After a particular point of time, they will be reaching a thermal equilibrium. Next point says the average distance of electrons' free movement between the collisions is known as the mean free path lambda. Again, this is a definition which was discussed in the chapter Electronic Materials. Here you can say that, suppose there are two atoms, two electrons which are colliding. So they collide and they move. So total distance they travel after the collisions, if the average of this distance is taken, we get the mean free path lambda. Next assumption of the Drude model is, after the collisions, the electrons move in random directions with a speed which depends on temperature of the region where the collision had occurred. Why do we say it depends on the temperature? Based on this point, it can be said that hotter the region, higher is the speed of the emerging electron. Because there are collisions that results in heat. Wherever there is a collision, there would be heat. Now, this movement of electrons will be from a higher temperature to a lower temperature, because we all know that heat always flows from higher to lower temperature. After the collisions, these electrons move in random directions and their speed is proportional to temperature. Moving ahead, let us discuss the applications of Drude model. So, currently what we have discussed were the assumptions in which particularly the kinetic theory of gases was considered. It was considered that electrons move like free molecules of gas. Now let us see what are the applications of Drude model, or I can say what are the parameters or properties which this model explains. So starting with the first property, we have electrical conductivity and Drude model. What do you mean by the term electrical conductivity? Electrical conductivity is a property which allows easy flow of charge carriers. I'm not using the word electrons here because we are discussing with respect to semiconductors and they have holes as charge carriers as well. So that is the reason I said it is the property which easily allows the flow of charge carriers. Conductivity is represented by the term sigma. So let's see how electrical conductivity is explained by Drude model. Just have a look at the diagram. In this diagram, what is shown? It is just a conductor shown with a flow of charge carriers. Cross-sectional A is shown. Now we know that the current density, because if we have charge carriers flowing across a particular area, there will be a flow of current, and this current with respect to area will give us the current density. What is the direction of this current density J? It will always be perpendicular or normal to the cross-section area. The number of electrons crossing the area A in a particular time dt will be NAV dt. This is how we define current. So on the basis of this, I can say if the number of electrons is NAV dt, I will be having the charge crossing the area A in dt, in the time interval dt is NEVA dt. We multiply it by the charge of electron. So we get the equation J is equals to minus NEV. Now we know that electrons drift in opposite direction of electric field and the drift velocity is given by V is equals to minus NE tau by N. Again, you have a negative sign in this equation which indicates that the drifting is in the opposite direction of electric field. And I can substitute the equation of velocity from this equation in the previous equation and I will be getting J is equals to NE square E tau by N. Now we know that J is related to conductivity as J is equals to sigma E. So if I compare these two equations, I will be getting sigma is equals to NE square tau by M, and this equation which is derived on the basis of assumptions of Paul Drude is what is known as Drude conductivity. And this is the equation which, if you remember, we had already derived while covering the topic of free electron theory. So this was the first application which is based on Drude model. Now let us see what is the next one. It is Hall effect and Drude model. You remember this term Hall effect? We had discussed in the chapter measurements. What is Hall effect? To be very brief, I can say if there is a current carrying conductor and if you apply a magnetic field to this current carrying conductor in a direction perpendicular to the flow of current, you will be getting voltage across the conductor, and this developed voltage or potential difference is what is known as Hall voltage. So first let's see what exactly this Hall effect is. It is known as the generation of potential difference across an electrical conductor when a magnetic field is applied in a direction perpendicular to the flow of electric current. Let's understand with the help of a diagram. In this diagram, you can see there is a current which is entering this conductor, and there is a magnetic field which is being applied perpendicular to the direction, to the flow of current. So I can just explain that. Suppose I say my index finger is pointing the direction of current, my thumb points the direction of magnetic field. So these three fingers will point the direction of electron movement. So if electrons are moving across one direction, there will be a potential setup which is represented as V Hall or VH, and that is what is the meaning of Hall effect. So in this particular direction, I can say my current is along the x-axis. The magnetic field we have applied is along the z-axis. It can be either positive or negative z-axis. Let's see how Hall effect is explained by Drude model. The electric field induced, it must cancel the Lorentz force which acts in opposite direction. Right? Why is this? There will be a Lorentz force because there was already a flow of electrons and a magnetic field was applied perpendicular to it, and that is the reason Lorentz force acts. So whatever is the electric field set up should cancel out this Lorentz force. This Lorentz force is a sum of magnetic and electric forces on the charged particles, and this is given by the equation FL indicates Lorentz force is equals to QE plus QVB. This is the equation where QE denotes the electrical force on the charged particle and QVB here denotes the magnetic force on the charged particles. So I can have the magnitude of Hall voltage calculated as VH is equals to RH JX BZ. VH here denotes Hall voltage, RH denotes the Hall coefficient, which is defined as 1 upon NE. 1 upon NE means N is the number of electrons per unit volume and E is the charge of electrons. I have written JX because the current is along the x-axis and BZ because magnetic field is perpendicular. So this is how I can say that Hall effect is also explained on the basis of Drude model because that explains the motion of electrons on the application of magnetic field and current both. Moving on to the third application of Drude model, which is known as the Wiedemann-Franz law and Drude model. What do you mean by the word Wiedemann-Franz law? If you remember, Wiedemann-Franz law was discussed in the chapter Electronic Materials. Wiedemann-Franz law is a law which relates thermal and electrical conductivities both for a metal. Why? Because metals or conductors, they are said to be good conductors of heat and electricity both. If I say they are good carriers of current, they are good carriers of heat as well, where heat flows from a higher to a lower temperature. We had also discussed and derived the equation of thermal conductivity, capital K. So now let's see what exactly Wiedemann-Franz law is. So this law states that for any metal at a given temperature, the ratio of thermal to electrical conductivity is a constant L, which is known as the Lorentz number. We had derived the equation K upon sigma is proportional to T, where removing the proportionality sign, we introduce a constant that is known as the Lorentz number. So I have this equation K upon sigma is equals to LT, where K denotes my thermal conductivity, sigma denotes my electrical conductivity, L is the Lorentz number and T is the absolute temperature. Next, substituting the equations of K and sigma based on the Drude model, because on the basis of Drude model we had derived both the equations. So equation of K is NV lambda upon 2, where N is known as the charge density, V is known as the velocity of charge carriers, the thermal velocity, Kb is the Boltzmann constant and lambda is known as the mean free path. And the equation of sigma, this should also be in terms of kBt. So that is Ne square lambda V upon 3 kBt. So based on these two equations, if I substitute these two equations in the equation K upon sigma, let us see what we get. We have K upon sigma is equals to 3 kb square T upon 2 E square. Just have a look at this equation. On the right hand side, apart from the term T, that is absolute temperature, all other terms are constants. 3 by 2 is a constant. Kb, that is Boltzmann constant, which has a value 1.38 into 10 raised to minus 23 joule per Kelvin, is a constant. And E means charge of electrons, that is 1.6 into 10 raised to minus 19 coulomb, is also a constant. And this entire constant can be denoted as L, that is Lorentz number. So this was what we derived in Weidemann-Franz law, and basis on this assumption of Drude model only, we have the equation K by sigma is equals to LT. So with this, our third application gets completed. Now let's see the fourth application of Drude model, which says optical reflectivity of metals and Drude model. What do you mean by the term of optical reflectivity? It deals with the interaction of metals and light. Light is an electromagnetic wave in the form of a transverse plane. What is light? Light is nothing but an electromagnetic wave. You can say light travels in the form of a transverse wave, which is formed of crests and troughs. So it is nothing but an electromagnetic wave only traveling in a transverse plane. So electric field of light propagating in z direction is given by. Now, because it is an electromagnetic wave, wherever we have light traveling, there will be a surrounding electric field of light, which in the z direction is given by the equation epsilon as a function of z and t is equals to epsilon naught e raised to I into bracket n minus ik into z, where we have n is known as the refractive index. What do you mean by the term refractive index? N is equals to c by v. It is the speed of light upon speed of light in any material. So that defines the ratio of speed of light. K is known as a parameter which defines attenuation. Attenuation means the absorption, the total loss when light is striking any material. And epsilon naught is the amplitude of light in the xy plane. Because we are defining electric field along the z direction, we take the amplitude along the xy plane, that is along the remaining two axes. Using the dielectric constant of the material, we have the equation epsilon zt, that is the electric field along the z axis is equals to epsilon naught e raised to I omega under root of epsilon by c into z minus omega t. An electron with electric field from electromagnetic wave moves according to this equation, where we have m into d square x by dt square. It is nothing but ma, which indicates force, that is equals to minus e epsilon e raised to minus I omega t. So this electron undergoes a positional displacement in a periodic manner due to the electromagnetic radiation, and this leads to the changing dipole moment, which is indicated by minus e xt as a function of time. So you can say a basic reflectivity equation or the basic interaction of light can also be described by the Drude model. So with this, I end the applications of Drude model. So in today's video, we have discussed what is Drude model, what are the assumptions on which the Drude model was based, and some of the applications of Drude model. Let me be very clear. Drude model, though explained many properties, it had certain disadvantages due to which the Drude model failed, and the next theory, that is Sommerfeld's theory, was proposed. Hope you have understood all the topics I discussed very well today. I will be starting with the last topic of the chapter, that is Fermi's golden rule and exciton, in my coming video. Till then, take care. Thank you.